Hello. So after reviewing and after learning the basics of linear modeling, we will now be discussing some challenging models or some algorithms or some patterns that we use to model very difficult linear problems. So today we will be discussing 3 of the special transformations that we use in order to model some LP formulations, which will be fractional modeling, modeling an absolute value, and modeling a maximin or minimax example. So we call this lecture as LP tricks, or some transformations that we use in order to properly model some algorithms. So we will be starting with fractional modeling. Fractional modeling involves LPs with an objective function stated as a fraction. If you notice, all our previous examples have all had objective functions that are all linear and simply a simple equation. So what do we do now if our objective function is expressed as a function? Or the general notation is maximization of the numerator C transpose X plus alpha all over the denominator D transpose X plus beta. C and D are the coefficients of our decision variables X, while alpha and beta are our constants in the objective function. In order to properly transform a fractional objective function to a linear model, we substitute T is equal to 1 over D transpose X plus beta, or T is equal to 1 over the value of your denominator. Y is therefore equal to Tx. So we change our decision variable X to a decision variable in Y, which is expressed in terms of T and X. Then our new linear programming formulation will be maximization of C transpose Y plus alpha T, with your constraints changing as D transpose Y plus beta T is equal to 1, and your regular constraints AY minus BT is less than or equal to 0, with Y and T all being greater than or equal to 0. To better illustrate this transformation, we will do this with an example. On the left-hand side, you will see the transformation, and on the right-hand side, you will see our example. So for this example, we will be transforming the fractional objective function max z is equal to 2x1 plus 3x2 plus 6 over 4x1 minus 2x2 plus 1. Given the transformation, we note that the new variable t is equal to 1 all over 4x1 minus 2x2 plus 1. And we say that y sub I is equal to t times x sub I. Given this transformation, we can rewrite our new objective function as max z is equal to 2y1 plus 3y2 plus 6t. Now, why is this transformation valid? Let's try looking at our original objective function and try to separate it for each term. We will see that we can rewrite our original objective function as max z is equal to 2x1 all over 4x1 minus 2x2 plus 1 plus 3x2 over 4x1 minus 2x2 plus 1 plus 6 all over 4x1 minus 2x2 plus 1. Given this, and given our transformation, that t is equal to 1 over 4x1 minus 2x2 plus 1, and that yi is equal to txi, we can now note that this whole term is simply x1 all over 4x1 minus 2x2 plus 1, and it can be transformed as t times x sub 1, which, based on our transformation, is equal to y sub 1. Therefore, the first term can be rewritten as 2y sub 1. The second term can be rewritten as 3y sub 2. And the last term of the objective function can be rewritten as 6t. From here, we add the additional constraints of 4y1 minus 2y2 plus t is equal to 1, which is simply this transformation. And we also note our second transformation of the transformation of our constraint into y sub 1 plus 3y sub 2 minus 5t is less than or equal to 0. So with the new transformation, or with our transformation, our LP formulation now will be transformed into a linear problem given max is equal to 2y sub 1 plus 3y sub 2 plus 6t, given the constraints 4y sub 1 minus 2y sub 2 plus t is equal to 1, and y1 plus 3y2 minus 5t is less than or equal to 0, with y sub 1, y sub 2, and t all greater than or equal to 0 using the transformation. Now let's solve another example. Given the objective function, fractional objective function, max is equal to x1 minus 2x2 plus 4x3 minus 3 all over 2x1 plus 2x2 minus 6x sub 3 plus 9. Given the constraints x sub 1 plus 2x2 plus 3x3 is less than or equal to 7, and 2x1 minus x2 plus 6x3 is less than or equal to 10. Again, we simply note the transformation needed. We let t be equal to 1 over the value of our denominator, or 2x1 plus 2x2 minus 6x3 plus 9. And we note that y sub I is equal to tx sub I. Again, using this transformation, we are now able to transform our fractional objective function into a linear problem. It will now be max z is equal to y sub 1 minus 2y sub 2 plus 4y sub 3 minus 3t, given the constraints 2y sub 1 plus 2y sub 2 minus 6y sub 3 plus 9t is equal to 1. Again, that is just the reiteration of our transformation. And you transform your constraints. Our original constraints will be transformed into y sub 1 plus 2y sub 2 plus 3y sub 3 minus 70 is less than or equal to 0. And the second constraint will be transformed into 2y sub 1 minus y sub 2 plus 6y sub 3 minus 10t is less than or equal to 0. With our y sub 1, y sub 2, and y sub 3, and the variable t are all greater than or equal to 0. Here we saw how we were able to transform a fractional objective function into a problem of a linear modeling. This can now be solved using the solutions to linear equations that we have studied before. We now move on to another transformation that we do for solving LP formulations, or how do we transform absolute values. Remember, absolute values take on only a positive value of the distance of the value from 0. So absolute values only take on positive values. However, we need to transform them into a linear transformation so that we are able to solve it using our linear techniques. So how do we transform an absolute value? For example, minimize z is equal to ax sub 1 minus b times the absolute value of x sub 2 plus c x3. In this example, a, b, and c are all integer constants of our decision variables. We notice that in this example, x2 is part of an absolute value function. Again, an absolute value can only take on a positive value, even if the x2 is negative. Therefore, we have to do a linear transformation in order to properly solve the problem. The transformation that we will be using is transforming x2 into x2 plus minus x2 minus. With this transformation, we are able to denote the value of x2, whether it is positive or negative. For example, if the actual value of x2 is equal to 2, the two values will take on x2 is equal to 2 minus 0, or based on our example, x2 plus will take on the value of 2 and x2 minus will take on the value of 0. If the actual value of x sub 2 is equal to negative 2, our x sub 2 transformation will take on the values 0 minus 2. In this case, x2 plus will take on the value of 0 and x2 minus will take on the value of 2. We are able to express our singular value into an expression of a difference of two positive values. With this transformation, we can now note that the absolute value of x sub 2 can be transformed into x2 plus x2 minus to denote that the absolute value will always be a positive value. Let's take a look at this case again. If x2 is equal to 2, the absolute value of 2 will be equal to 2. Therefore, x sub 2 plus will be 2. And x sub 2 minus will be 0. Therefore, the absolute value of x2 is still equal to 2. Looking at the second case, if x sub 2 is negative 2, the absolute value of x sub 2 will still be 2. But if you substitute our transformed variables, it will become the absolute value of x sub 2 is equal to 0 plus 2, substituting these values, and we still get a positive value for the absolute value function, even though x sub 2 takes on a negative value. So the proper transformation for absolute values is transforming the variable as a difference of two positive values and transforming the absolute value function as a sum of those positive values. Let us now transform this example. Minimize z is equal to 3 times the absolute value of x1 plus 4 times the absolute value of x2 minus 3x sub 3, subject to the constraints negative x1 plus x2 minus x3 is greater than or equal to 4, and 2x1 plus 3x2 minus 3x3 is greater than or equal to 9. Here we see that we have two variables that are inside the absolute value function. We have x1 and x2. Again, based on our transformation, we will let x1 or transform x1 into x1 plus minus x1 minus, and transform x2 into x2 plus minus x2 minus. And then we also transform the absolute value function of x1 into a sum of these variables, or x1 plus x1 minus, and the absolute value of x2 into the sum of x2 plus and x2 minus. From here, we now substitute these equations into our original LP formulation. In this case, that's going to be min z is equal to 3. The absolute value of x1 is transformed using this equation. So that becomes 3 times x1 plus x1 minus. But we transform the absolute value of x2 function using this equation, which is plus 4 times x2 plus x2 minus 3x3. No transformation is needed for x3. We now look at the constraints. So that's negative x1 And the transformation of x1 is given by this equation. So that's negative x1 plus minus x1 minus plus transformed using this equation plus x2 plus minus x2 minus x3 is greater than or equal to 4. And then the second constraint is 2. Again, the transformed equation of x1 minus x1 minus plus 3 times the transformed equation of x2 plus minus x2 minus 3x3 is greater than or equal to 9. And all our variables, x1 plus, x1 minus, x2 plus, x2 minus, and x3 are all greater than or equal to 0. So again, this is how we transform absolute value functions in our objective function. But the next question is, how about if our absolute value functions are written in our constraints? For example, instead of having normal constraints, we are given the absolute value of a sub x1 plus b sub x2 plus c sub x3 is all less than or equal to a certain value. The transformation is simple. We simply denote that ax1 plus bx2 plus cx3 is less than or equal to d, and add another constraint negating the whole equation, negative ax1 plus bx2 plus cx3 is less than or equal to d, and then transform it. So if we wish to transform the constraint 2x1 minus 8x3 plus 3x3 is less than or equal to 12, again, it's absolute value of 2x1 minus 8x sub 2 plus 3x sub 3 as less than or equal to 12. We simply copy the equation 2x1 minus 8x2 plus 3x3 is less than or equal to 12. And we also get the negative of the equation, negative 2x1 minus 8x2 plus 3x3 is less than or equal to 12. Therefore, this is the proper transformation of constraints written as absolute value functions. We now move on to our last special transformation, or the minimax or maximin transformation. Minimax or maximin is usually used in game theory or in some decision making or in some decision algorithms for LP formulation. So, how do we transform, for example, minimax of three functions, f of x, g of x, and h of x? If you recall, in our linear programming examples, we can only have one objective function. So it's either maximizing or minimizing something. So how now do we deal if our objective function is given as a combination of a minimum and maximum, or a minimization and a maximization problem, such as minimax, or a combination of maximization and minimization, which is a maximin problem? Let's look into the minimax problem first. So if you're given minimax of three functions, f of x, g of x, and h of x, with your normal constraint, we introduce a new variable t, which will help us solve the problem. In a minimax example, we take in your main goal of minimizing, and we say that our goal is to minimize t. Minimizing t will be the maximum of these three equations. So, if we want the maximum value of these three equations, f of x, g of x, and h of x, we want t to be the highest among these values. So we say that t is greater than or equal to f of x, t is greater than or equal to g of x, and t is also greater than or equal to h of x. With these three new equations and with the new variable t, we are able to get the maximum value among the three functions that we want to know, and we minimize that value as much as possible. And then, of course, we have your regular constraint. Ax is less than or equal to b. We want to maximize the three functions f of x, g of x, and h of x. And your normal constraint ax is less than or equal to b. Again, we introduce a new variable t, and we want to maximize t. And then we want to get, and t will be the minimum of the three equations. Therefore, f of x, g of x, h of x will all be greater than or equal to t. With these three additions, or these three new constraints and the new variable t, we are able to get that t is the minimum value among those three equations, and we maximize that value. And of course, your normal constraint ax is less than or equal to b. Let's take a look at one example. So we want to minimize the maximum among three equations, 2x1 plus 4x2 and 5x1 minus x2 and 3x1 plus 2x2, subject to the constraint that x1 plus x2 is less than or equal to 20. Again, in order to do this, we introduce a new variable t to help us with the equation. Since this is a minimization function, we wish to minimize t, and t is the maximum among these three equations. Therefore, we note that 2x1 plus 4x2 is less than or equal to t. Again, t has to be the maximum value of the equations. 5x1 minus x2 is less than or equal to t. T again is greater than the equations. And 3x1 plus 2x2 is less than or equal to t. And our normal constraint x1 plus x2 is less than or equal to 20. Therefore, the transformation of this minimax example can be rewritten as these LP formulation. Now let's take a look at an example of a maximin problem. We want to maximize the value of the minimum of the equations 5x1 plus 3x2, 4x1 plus 2x2, and 6x1 minus 3x2, subject to the constraint that x1 plus x2 is greater than or equal to 30. So again, we introduce a variable t to help us transform the maximin equation into an LP formulation. And we get, again, we want to maximize t, and t is the smallest among the three equations. Therefore, 5x1 plus 3x2 is greater than or equal to t. 4x1 plus 2x2 is greater than or equal to t. And 6x1 minus 3x2 is greater than or equal to t. Again, your normal constraint of x1 plus x2 is greater than or equal to 30. So again, we are able to transform the maximin problem into a linear problem using the simple transformation. Now that we have discussed these formulations or these transformations, let's try to look at an example that uses two of these three transformations. Let us consider the city of Kasama, who has 4 barangays and is plotted on an arbitrary coordinate system. The centers of each barangay is given on the table. The mayor of Kasama plans to put up one fire station inside the city. He wishes to minimize the maximum distance that the fire station travels to each barangay. Since the roads in Kasama only run in a north-south and east-west direction, assume that the fire truck can only travel rectilinear distances. And then we are given the table of the 4 barangays and the location. So to elaborate on this example, we wish to note where to put the fire station in the barangay such that it minimizes its maximum travel distance in case a barangay needs help in putting out a fire. So, without transformation, we are actually doing a mini-max problem. Let's formulate this as a formulation without any transformations yet. Again, if you recall, the first thing we asked in order to formulate a linear problem is what do we want to know. In this problem, we want to know the location of the fire plant, of the fire station, in terms of an xy coordinate. So we let x be the x coordinate of the fire station and let y be the y coordinate of the fire station. Therefore, our optimum value will be a coordinate of xy, which is where we will put our fire station. We want to minimize the maximum distance. And also given in the problem that that the roads in Kasama can only travel north to south or east to west. Therefore, all roads are rectilinear, or we can only go up and down, left or right, but not go diagonally. This now proves as a challenge since we are also getting the distance. Distance will always be a positive value. Therefore, we note that the distance of fire station from barangay A will be given as the absolute value of the x distance, x minus 1. 1 is the x coordinate of barangay A plus y minus 7. The distance from barangay B will be given by x minus 2 plus the absolute value of y minus 5. From barangay C, that's x minus 3 plus the absolute value of y minus 3. And from barangay D, that is going to be the absolute value of x minus 6 plus the absolute value of y minus 4. If we let d sub I be the total distance from barangay I to the fire station, the distance or this equation will be equal to d sub A. This will be equal to d sub B, d sub C, and d sub D. Therefore, we now have the equations, but we are looking into the minimization of the maximum distance. Therefore, our objective function will be minimize the maximum distance, which is d sub A, or d sub B, or d sub C, or d sub D. This is the complete LP formulation, or the complete problem formulation of the problem. Here we see that we have a minimax problem and that we also have an absolute value transformation. Therefore, we have to do two transformations in order to properly formulate our LP to make it linear. Let's start with the absolute value transformation. Again, note that we have several x values, or we have several absolute values. So we now use the minimax transformation and the absolute value transformation in order to properly transform our problem into a linear problem. In order to do this, we will be introducing new variables. Let VI be the distance in x of barangay I, and we let WI be the distance in y of barangay I. Now, in this example, we look at the x values first. We now get the x distance of barangay A, which is given by the absolute value of x minus 1. Therefore, our transformation, if you recall, is x minus 1 is equal to VA plus minus VA minus. The absolute value of x minus 1 will be given by VA plus VA minus. We now get the y distance of barangay A, which is given by the absolute value of y minus 7. We will now be using the variable w since we are concerned with the y distance. Therefore, y minus 7 is equal to WA plus minus WA minus. And the absolute value of y minus 7 is equal to WA plus WA minus. This is only for barangay A. Let's now transform the value of barangay B. Barangay B is given by the absolute value of x minus 2 and the y distance of the absolute value of y minus 5. Therefore, we rewrite this as barangay B. The x distance is given by the absolute value of x minus 2, or x minus 2 is equal to VB plus minus VB minus, and the absolute value of x minus 2 is equal to VB plus VB minus. For the y distance, it's given by the absolute value of y minus 5. Therefore, y minus 5 is equal to WB plus minus WB minus, and the absolute value of y minus 5 is given by WB plus WB minus. For barangay C, it will be noted as x minus 3 is equal to VC plus minus VC minus, and the absolute value of x minus 3 as VC plus VC minus, and for the y distance, it's given by the absolute value of y minus 3, and y minus 3 is equal to WC plus minus WC minus, and the absolute value of y minus 3 is given by WC plus WC minus. We now go to barangay D. The transformation for the absolute value of x minus 6 will be given by x minus 6 is equal to VD plus minus VD minus, and the absolute value of x minus 6 is equal to VD plus VD minus, and y minus 4 is equal to WD plus minus WD minus, and the absolute value of y minus 4 is equal to WD plus WD minus. So we are now able to transform your absolute values into values with only positive values, and it will all be linear in nature. And then, what we do now is we transform your objective function. Again, our objective function is min-max of dA, dB, dC, and d sub d. Again, in order to transform a minimax, we introduce a new variable t, and we wish to minimize t. Min t, that's our objective function, dA is less than or equal to t, dB is less than or equal to t, dC is less than or equal to t, and d sub d is less than or equal to t. We also include all our absolute value transformations. So we start with our transformation of x minus 1. Therefore, we note that x minus 1 is equal to VA plus minus VA minus. Y minus 7 is equal to WA plus minus WA minus. We also include your transformations for our other variables. X minus 2 is equal to VB plus minus VB minus. Y minus 5 is equal to WB plus minus WB minus. X minus 3 is equal to VC plus minus VC minus. Y minus 3 is equal to WC plus minus WC minus. X minus 6 is equal to VD plus minus VD minus, and Y minus 4 is equal to WD plus minus WD minus. However, we're not yet done. We just included our transformations, but we have to denote that D sub A is equal to the sum of the absolute values in A, D sub B is the sum of the absolute values in B, and so on and so forth. So, using our transformations, our previous transformations, we have our constraints as d sub a is equal to the absolute value of x minus 1 plus the absolute value of y minus 7, which we have previously transformed. Therefore, d sub a is equal to va plus va minus plus wa plus wa minus. D sub b is equal to v sub b plus v sub b minus plus w sub b plus w sub b minus. D sub c is equal to vc plus vc minus wc plus wc minus. And lastly, d sub d is equal to vd plus vd minus wd plus wd minus. And of course, we do not forget our non-negativity constraints such that d sub I, x, y, v sub I plus, and v sub I minus are all greater than or equal to 0. Therefore, we are able to transform our formulation, which includes a minimax and an absolute value problem, into a formulation that is all linear in nature. This allows us to use our algorithms to properly solve the problem. That concludes our discussion for LP transformations or LP tricks. Just to review, we discussed the LP transformation of a fractional objective function value, of absolute values, and of minimax and maximin problems. I hope you learned something today and that you are able to apply this in your future endeavors. Thank you.